Alright, in this section we're going to learn how to compare series together. So the way that we use these tests, these comparison tests, we're always given some series in these problems. They give us a series, they want to know, does it converge or diverge? If we're going to use a comparison series, what we have to do is look at that series and say, you know what, that seems kind of like this other series, one series that we could sort of think of, and where we know what that series does. And we have to say, you know what, it's kind of like this series, and I think they behave the same way. So I think that this is going to, diverge like this series I know, or I think it's going to converge like this other series I know. There are two comparison tests. The first is called the direct comparison test. I don't want you to worry about AN versus BN, which ones we call A's or which one we call B's so far. Just yet. I don't want us to get caught up in subscripts and whatever, but here's the gist of the direct comparison test. Part 1 says, suppose I know that this test of the BNs converges, and I know that this other test with the ANs, they're all less than the BN terms. Both terms of these series, they're all positive terms. And I know that the AN terms are all less than the terms of this other series that converges. So that BN series that converges kind of is pushing down this other series. And if that BN converges, there's no way the AN series could blow up, right? It also has to converge. The other way to use the direct comparison is to say, look, suppose I know that the terms of this series that I'm looking at, they're all bigger than the terms of this other series, and I know this other series diverges. Then that means that that divergent series is sort of preventing the series that I'm looking at from converging. The series with the ANs blows up, and my terms are all bigger than that series. That means that my series here, this series also has to blow up. We're going to do some examples here to kind of show you what I mean. And what we're doing, when we use this is we're kind of writing an argument. We're picking a series to compare it to. We're saying, I know what this series does, and here's why I know that. Maybe it's a P series, maybe it's a geometric series, but it's something where I can say I know it diverges or converges, and I can tell you why. And then how do I use the direct comparison test? How do I cite that test to draw a conclusion about the series that I'm interested in? So in this first example, our series is defined by the terms 1 over 2 plus 3 to the n. So I want to pick a series. It's up to me to pick a series to compare it to. So I'm going to compare this series to this series where n starts from 1, goes to infinity, just 1 over 3 to the n. Really similar, right? All I'm doing is ignoring that 2 plus, that term of 2 in the denominator. Now I need to be able to say what this series does. And looking at this series, if I rewrite it, 1 over 3 to the n, that's equal to 1/3 to the n. This is a geometric series. It's geometric series where r is equal to 1/3, and that is less than 1, and that means it converges. So I've picked a series to compare it to, and I know that my comparison series converges. Now let's try to apply this. We're going to apply term for term the series in the terms in the series they gave us and the terms in the series I chose. So let's observe that 1 over 2 plus 3 to the n, this is less than or equal to 1 over 3 to the n for all values of n, for all n greater than or equal to 1. Term for term, the values of 1 over 2 plus 3 to the n, they all have to be less than 1 over 3 to the n. That's pretty simple to see because the numerators are the same. And 2 plus 3 to the n is greater than or equal to 3 to the n. So now the terms of my series, they're all less than the terms of a convergent series. And so I'm just going to write that out and write my conclusion and say, since the terms of this series are all less than the terms of a convergent series, it follows that our series has to converge. So this is what it's like to use a direct comparison test. This is sort of a simple, kind of straightforward application. Note that it's on us to pick the comparison series. I had to be able to look at the series they gave us up here and then say, you know what, I'm going to compare to this series. I had to come up with that series. And usually we just take our cue based on something that it looks similar to. Sometimes it's not quite that simple, but a lot of the time we can kind of just say, you know what, I'm going to simplify this series a bit. You know, kind of, it certainly made it easier to deal with if I just didn't have that term of 2 in the bottom, and I was able to make a simple series and say, I know what happens to this, and I think these are going to behave the same way. All right, let's take a look at this next example. Here our series is 1 over 2 plus root n. Now, you know, taking our cue based on what we did last time, we might try comparing this with the series 1 over root n. If we rewrite that series, it looks like 1 over n to the 1/2. This is a p series where p is less than 1, less than or equal to 1, which means it diverges. And our hunch is that we think that this series is awful similar to this other series, is similar to the 1 over root n series, so we think that it'll probably diverge. So we want to try to make a comparison to show that. So let's observe that the terms, 1 over 2 plus root n, this is less than or equal to 1 over root n for all values of n. And that's like the same argument we made last time, right? I mean, the numerators are the same, and the denominator on the left is a little bit bigger, right, than the one on the right, so that fraction has to be smaller. So this is true for all n greater than or equal to 1. So what we've shown is that the terms of this series, or the terms of our series they gave us, are all less than the terms of a divergent series. Now here's the problem. If the terms of our series are all less than the terms of a divergent series, that means that this is inconclusive. It could mean that they're all less than this divergent series. Maybe they're so much less than the divergent series that the series converges. Or maybe they're less than this divergent series and it still diverges, but maybe more slowly. The point here is that showing that your terms are less than something that diverges doesn't allow you to conclude anything. The direct comparison test works if you could show that your terms are all greater than something that diverges or all less than something that converges. So now we're going to start again, right? Let's try again. Comparing to the series 1 over root n didn't work. Now, that doesn't mean that our idea to think about comparing to the series whose terms are 1 over root n isn't worthwhile, because look, the terms of our series are very similar to that series 1 over root n, and it would stand to reason that they might have similar behavior. It's just that if I use the direct comparison test with that series, it doesn't allow me to conclude anything. But I still hold on to the hunch that the series they've given us here is going to diverge, because I think it does the same thing as this 1 over root n. So what we're going to do, if we're going to use the direct comparison test, I have to compare it with something that diverges, and I have to be able to show that our terms are all maybe greater than something that diverges. So let's try again, and we'll compare with the series whose terms are 1 over n. This diverges. It's the harmonic series. It's a p series where p is equal to 1. So now, if the direct comparison test is going to be conclusive for us here, we're trying to see, is 1 over 2 plus root n, is this greater than, and that's a question, is this greater than 1 over n? So I'm going to work with this inequality, treating it, as a big question mark, and then see what we can conclude in the end. I'm going to clear denominators, so I'm going to multiply both sides by n times 2 plus root n. Now, because n times 2 plus root n, those are both positive, when I multiply both sides by that, the sense of the inequality will be preserved. So this will look like n greater than or equal to 2 plus root n. Still a question mark. I'm going to subtract 2 and subtract root n from both sides. So we get n minus root n minus 2, and we want to know, is this greater than or equal to 0, or for what values is it greater than or equal to 0? The left side, it might not look it at first, but it's actually a quadratic. It's a quadratic in root n, because n is the square of root n, and so this will actually factor and it will look like root n minus 2 and root n plus 1. Now, root n plus 1, this is always positive. And root n minus 2, this is certainly positive when n is greater than 4. And it stays positive, right? As long as n is bigger than 4, that's positive. So that means that this inequality holds as long as n is greater than 4. And in fact, I would say the inequality or equal to always holds when n is at least as big as 4, greater than or equal to 4. So this fraction, 1 over 2 plus root n, is greater than or equal to 1 over n for all values of n that are at least as big as 4. So what we've shown is, while this inequality doesn't hold for the values 1, 2, and 3, it does hold for all but finitely many terms in the beginning. So if that comparison holds for all but finitely many terms, then those series still have to do the same thing, because if I say that I've got this series that converges and then I add 3 more terms, 3 more finite terms to it, it still has to converge. So let's sort of get this argument down in words. For all but finitely many terms. The terms of our series, 1 over 2 plus root n, are all greater than the terms of a divergent series. And this is a comparison that works, right? If you're showing that your terms are all greater than the terms of a divergent series, that means that your series has to diverge. All right, so we did some direct comparison. Now we're going to look at another comparison test. We call this one the limit comparison. And again, we're looking at a series. We're comparing series whose terms are all positive, or at least non-negative. So let's say I've got a couple of series. The terms are both non-negative for all series, for all terms. If I compare if I make a ratio of like the terms of the corresponding series, the corresponding terms in the series, if that limit is finite and positive, then those two series both have to do the same thing. They either both converge or they both diverge. This is a really convenient test for trying to see, like, compare a series that might be kind of algebraically messy to a nice simple p-series. And it helps us practice our limit taking skills. So now let's do an example. Let's say we want to know what's going on with this series whose terms are n2 to the n plus 5 over 4n cubed plus 3n. That is a pretty messy series. So what I'm going to do is I'm going to ignore all but the highest degree terms in both the top and the bottom, meaning I'm going to ignore these small bits at the end. I'm going to ignore them, and I don't mean like ignore them and pretend they're not part of my series. I'm going to ignore them for the purposes of choosing my comparison series. So I'm going to focus on that n2 to the n over 4n cubed. And even the coefficient of 4, I'm going to ignore that. So I'm going to compare this series. I'm going to compare this with the series n2 to the n over n cubed. And in fact, even this one, of course, we can simplify, right? N over n cubed means I could cancel an n, and I've got an n squared in the bottom. So I'm going to compare this to the series 2 to the n over n squared. Now, an important part about performing any comparison test is that you have to know what your comparison series does. In the direct comparison test, we compared one series to a geometric series, so that was easy. Another one we compared to a p-series, so that was easy. This one, we could say we know what this series does. We know that this series diverges, and it diverges by the nth term test. If you find the limit of 2 to the n over n squared, you'll find that that limit is not 0. In fact, it's infinite. 2 to the n exponential growth outpaces polynomial growth every time. So this diverges by the nth term test. So now what we're going to do is look at the limit as b approaches infinity, and we're going to just form a ratio of the terms of our series with the terms of the comparison series. So I'm going to start with our series that they gave us, n times 2 to the n plus 5 over 4n cubed plus 3n. And I've got to divide that by the terms of this series. So I'm going to multiply by the reciprocal. All right, we're going to do some algebra. So I'm going to just look at this as a single fraction. Up top I have n squared times n2 to the n plus 5. On the bottom, now I could factor out an n from the bottom here. So I'm going to take out an n. 4n squared plus 3, and then I have a 2 to the n. So we can cancel that factor of n with one of these factors. So we've got n 2 to the n, whoops, n 2 to the n plus 5, n 2 to the n, oh, plus 5n. I'm going to distribute that n over, and sorry, that's an n squared because we have an n times an n here. Let me bring that down. Over 2 to the n times 4n squared plus 3. All right. It still looks a little messy, right? So I'm going to use a little algebra technique here. I'm going to multiply both the top and the bottom by 1 over the highest power of n, and also that 2 to the n. Get that out of there. So 1 over 2 to the n times n squared. Up top, if we distribute, distributing this fraction, 2 to the n, n squared 2 to the n times 1 over 2 to the n squared, that's 1. And distributing to the 5n, you'll cancel one of those n's, so we get 5 over n2 to the n. On the bottom, let's see, the 2 to the n cancels straight away. And then I'm just going to distribute the 1 over n squared that's left through the parentheses, and we get 4 plus 3 over n squared. Now as n approaches infinity, for some reason I have written this as a limit as b approaches infinity this whole time. Why didn't anybody tell me that? I must have the improper integrals on my brain right now. So we're looking at the limit as n approaches infinity. Now as n gets huge, these fractions, 5 over n2 to the n, that certainly approaches 0. 3 over n squared, that approaches 0. And so this whole limit is 1/4. And here's the thing, we found the limit. The next thing we have to do is make the observation. We need to explicitly state that we're observing that this is both finite and positive. Now, you might wonder, isn't it obvious that it's finite and positive? Why do I need to say that? Yeah, it's obvious that 1/4 is finite and positive. We need to say it because there's going to be other convergence tests where we find other limits, and we need to observe different things about those. So we need to know what it is we need to look at when we find this limit. How do we make our decision after we've evaluated this limit? And so we're going to explicitly state this is finite and positive. That's what allows us to conclude that our series that they gave us must do the same thing that our comparison series does, and our comparison series diverged. So that means that our series diverges as well. All right, so that last example took quite a bit of algebra, you know, kind of working out that limit. A lot of the time when we use the limit comparison test, it could be pretty quick. For example, let's say we want to figure out what happens to this series 1 over 3n squared minus 4n plus 5. So those are the terms of this series. What we want to do is quickly pick a comparison series and evaluate the limit, right? We're going to perform the limit comparison test. And what we're going to do is just basically ignore all but like the highest degree terms. I want to make a nice quick p-series comparison. And so I'm going to compare to the series whose terms are 1 over n squared. I'm ignoring that 4n and 5, and then I'm even ignoring that coefficient on n squared. I'm ignoring that coefficient because this series I don't have to perform a test with. This is a p-series. It converges. Because p is equal to 2, which is greater than 1, so it converges. Now I'm going to look at the limit as n approaches infinity, and I'm going to have an over bn, the terms of one series divided by the terms of the other. And it does not matter which one you decide to start with and which one you divide by. Both, regardless of which one goes on top, you'll reach the same conclusion. So I'm going to take our given series, divide by the terms of our comparison series, so times n squared over 1. I'm going to write it as a single fraction first. Plus 5. I don't know why I wrote plus 1 there. So this is our limit that we need to evaluate, and a simple a simple algebraic move will work here. I'm going to multiply the top and the bottom both by 1 over n squared. And we get on top 1. On the bottom we get 3 minus 4 over n plus 5 over n squared. The 4 over n and the 5 over n squared, those both approach 0 as n gets huge. So this whole limit is equal to 1/3. This is finite and positive. And that means both series have to converge, right? Our series is going to do the same thing that our comparison series did. So we can conclude that this series, whose terms are 1 over 3n squared minus 4n plus 5, that this converges. Let's try one more. We're going to figure out what this series does. The series they've given us has terms that are given by 1 over the square root of 3n minus 2. So I'm going to make this as simple as possible. I'm going to ignore that minus 2. I'm even going to ignore that coefficient on n there. And I'm going to compare with the series 1 over the square root of n, which we can rewrite as 1 over n to the 1/2. That's a p-series. P is equal to 1/2, which is less than or equal to 1, and that means it diverges. So now we're just going to set up a limit. It really doesn't matter which one goes on top, which one goes on the bottom. I'm gonna this time put the 1 over root n, and then divide by the terms of the given series. So root 3n minus 2 over 1. That's what I'll multiply by. Now I'm going to put this in a single fraction, so I have one radical over the other radical. But you can combine radicals under division. So this is going to look like 3n minus 2 over n. We can do the division. We can sort of split up this fraction over the subtraction up there. And if you do that and simplify, 3n over n is 3 minus 2 over n. And now this limit is pretty simple to evaluate. 2 over n, right, that approaches 0. So this whole limit is approaching the square root of 3. And what we're going to observe about this limit is that this is finite and positive. That means that our series has to do the same thing that our comparison series did. And so it's got to diverge.